like the name implies here, it's going to take us a little while, but when we're done, we'll have something that's pretty interesting. So we're going to start our story with two vectors. I'm going to say there's a vector u and a vector v. Vector u has components u1, u2, u3, and vector v has components v1, v2, v3. So one of the things you could do with these vectors, you could find the dot product. You can do u dot v, and a dot product, you simply multiply the x components and add that to the product of the y components, and then add that to the product of the z components. And when you're done, you get a scalar quantity. Sort of an important concept to understand. Dot product will take two vectors of the same dimension and bring them or map them onto a single value, a single scalar. Another product you can compute is a cross product, u cross v. And there's lots of fun ways to do that. A popular way to do it, though, is the determinant way, I, j, k. You make a little matrix out of these. I, j, and k are the unit basis vectors for 3-space. So we'll put the components of vector u here and the components of vector v here. And then we go to work on this determinant. So the way determinants work, you take the vector I and you cross out the column and row next to it, and whatever's left is called the minor of I. So that's how it works. So watch what I'll do. I'm going to undo those things, and this is going to equal, I'll do that one in red. So this is going to equal I times its minor, which is U1, U2, U3, V2, V3. If you remember, those were the 4 components that were left when I cross out the column with I and the row with I. And then I do it again with J. I cross out the column and row, and then whatever's left here. So I'll have U1, V1, U3, V3. So let's get rid of those lines there. So one little subtlety, you got to put a minus there. So it's minus U1, V1, U3, V3. And then lastly, plus K. You cross out the column and row with K. You take the thing that's left, and that's going to go over to here. So I'm just going to get rid of all that stuff. Here we go. You'll have U1, U2, V1, V2. And it turns out it's really easy to do the determinant of a 2x2 matrix. You just multiply these two together, like U2 times V3, and then you subtract what you get when you multiply the other two, V2, U3. And then you do minus J times, so you have U1, V3 minus V1, U3. And finally, you have plus K times U1, V2 minus V1, U2. And so this thing here is your cross product vector. If you want, you can write U cross V equals, and then write this all out like a vector. So you can see what I'm doing here with its components. And then finally we would have U1, V2 minus V1, U2. And it turns out there's a pretty special thing that happens if you find the length of the cross product. And that's how our story is going to start today. We're going to find the length of the cross product, and we'll end up with something pretty neat when we're done. It's just going to take a while. So we know when we take the norm of a vector that we square all its components. So we're going to take each of these components here and square them. And then we're going to add them together and take the square root. So what I'm going to do temporarily is just to avoid square roots, I'm going to square this. So we're just going to take each component squared and add them together. So if you square this one, for example, what do you get here? We'll keep this one red. So if we square this first one, you'll get U2 squared, V3 squared. You'll get two middle terms that are the same. So you'll have minus 2 U2 V3 V2 U3, and then you're going to plus V2 squared U3 squared. Okay, and then we just kind of sort of follow the same way, same thing we're going to do. We're going to square this binomial now. If we do that, we'll get U1 squared V3 squared minus 2 U1 V3 V1 U3. And then finally, we get a plus V1 squared U3 squared. See that here. That is this component. So just in case there's any ambiguity, that's my V and that's my U. All right. So finally, we'll use a third color. For this last one here, we're going to have a U1 squared V2 squared minus 2 U1 V2 V1 U2 minus V1 squared U2 squared. So safe to say this looks pretty bad to look at. And from here on in, it's only going to get worse because we're going to go for calculating the value of another expression, which may surprise you. Just be careful. I'm looking at one thing. This needs to be plus here, in case you noticed that. All right, so the next quantity we're going to compute is we're going to take the length of u times the length of v. I'm going to square that quantity also. So to a certain extent, you're really just trusting me about what we're doing here. And then at the end, this is all going to come together in some kind of nice way. So to get the length of a vector, you just square all its components. So you get u1 squared. You add them together. So it's the sum of the squares of the components. And you take the square root. And we're going to do the same thing for the vector v. v1 squared, v2 squared plus v3 squared. And since I'm squaring this whole thing, those square roots will disappear. And so what I'm left with really is just this u1 squared plus u2 squared plus u3 squared times v1 squared plus v2 squared plus v3 squared. And I have to multiply all this out. So let's do this in a color-coded way. I'm going to distribute the u1 onto these three terms first, the u1 squared, and we would get u1 squared v1 squared plus u1 squared v2 squared plus u1 squared v3 squared. And then what's left to do now is distribute the second term into all of these. So we'll get plus u2 squared times v1 squared plus u2 squared times v2 squared plus u2 squared times v3 squared. And then lastly, I need to distribute this u3 squared onto each of these three terms. So I'll get plus u3 squared v1 squared plus u3 squared v2 squared plus u3 squared v3 squared. So there's another scary looking quantity for you to consider. Okay, so here comes one more fun quantity we're going to compute. We're going to take u dot v and square that. So u dot v would be u1 v1 plus u2 v2 plus u3 v3. And if we're going to square it, we're going to just multiply it by itself. So I guess we'll write them both out so as to not lose track of things. We'll have u1 v1 plus u2 v2 plus u3 v3. And then the same thing again. and we're just going to work on this. So we could do this a number of ways. I think one thing we do is take this and we could distribute it across these three terms. We would get u1 squared v1 squared plus u1 v1 u2 v2 plus u1 v1 u3 v3. All right, let's go through in a color-coded fashion. So let's take this one now, this term, and distribute it amongst these three. So we will get plus u2 v2 times u1 v1. Isn't it nice how those line up? Plus, we'll have u2 v2, both of those squared. And then finally plus u2 v2 u3 v3. And then one more distributive property to do or calculate. So we'll have plus, looks like we're going to have a plus u3 v3 u1 v1, and then a plus u3 v3 u2 v2, and then finally we'll have a u3 squared v3 squared. And then some really cool things happen here. So what you'll notice is, for example, you'll see that these two terms are really the same. So you have two of those. Let's go with a different color. We have these two, which are really the same. And then finally, you have those two, which are really the same. So if we take the time to rewrite all of this, we end up with u1 squared v1 squared plus 2u1 v1 u2 v2 plus 2 u1 v1 u3 v3 plus 2 u3 v3 u1. I'm copying the same term over again. That's a mistake. This should be u2 v2 u3 v3. And then finally you have plus a u2 squared v2 squared and plus a u3 squared v3 squared. So what I really care about now are a couple of things. I care about this expression. I care about this whole expression here. And I care about this whole expression here. So let's put them all on one page and take a look at them. So here we are. We have all three things on a new page with the original expressions written next to them, what we calculated to get these crazy long expressions. And it's not immediately obvious, but there's a really cool relationship here. If you look carefully, if you take this first thing here and you subtract this thing, then you get that thing. So if you look at all the terms, you'll see them cancel. You'll notice, for example, all the two terms with 2 here turn into negatives down in the expression below because we're subtracting them. And you'll also notice that the u1 v1 squared, the u3 v3 squared, and the u2 v2 squared, both of those, all three of those are gone in that final expression. So that gives us sort of a cool fact to work with. So we can say the norm of u times the norm of v quantity squared minus u dot v squared equals that expression squared. We actually have a nice relationship here. We know from other proofs that u dot v, the dot product of two vectors, can be written as the length of u times the length of v times the cosine of the angle between the two vectors. And then you start to see something really pretty here on the left-hand side. This common factor. We can take out norm u, norm v, quantity squared, and be left with 1 minus cosine theta, cosine squared. And this is equal to the norm of u cross v squared. Well, so this thing is simply sine squared. And just like I said, this is a long story, but with an exciting ending. If we take the square root of the entire quantity, we end up getting norm u, norm v, times the sine of theta is equal to the length of the cross product. Now that is pretty cool. Then sort of as a cool follow-up to that, if you think of having two vectors, a vector may be u here and a vector v here, then you know that this distance here, this is the angle between them, can be found by finding the length of vector v times the sine of theta. Well, if you think about this length of our cross product, then we really have the length of a vector u times this expression, which can simply be thought of as the height of the parallelogram that's spanned by the two vectors. So that's the geometric interpretation of the length of the cross product. I hope you enjoyed that. Thanks for watching.